Good morning all of you. Today let us have the next lectures on river equilibriums, in which we will talk about the next part of the river equilibriums is that we will revisit regime relationship, we will talk about downstream hydraulic geometry and river meandering, and also the basic concept to the advanced levels, how the river equilibrium concept has evolved with the time. That is what I am going to present you. So, if you look at the next part, it is very interesting that I have taken a new book concept, which is a river training and protections work for railway bridges by Indian Railways of Institute of Civil Engineers, which is published in 2016. We will have some cross reference of this book about Indian knowledge about river equilibriums, river morphology, that the concept river characterization, regionalizations of river characterizations. These are the things are very detailed is given in this book, and I am going to follow this book as well as P.Y. Julian books. As you know it, many of the study has been done for the University of study has been done for the river Mississippi, and lot of experience on the Mississippi rivers and elsewhere. The combinations of both I am going to deliver the lectures for you. Now, we will look at the concept. If I look at the river has a n number of degree of freedoms. That means, we can visualize the rivers has the n number of degree of freedoms in terms of flow variables, in terms of sediment variables, in terms of meander channels, the river band, it has the variability. So, how do you do it? We start doing the river survey. So, we look it to the river survey, which earlier used to go to the field, conduct the river survey, measure the velocity, depth, width, perimeters, discharge, sometimes maybe the bed shear stress, bed material movements, all we can sediment load, the bed load part we can measure it. Also, they use the satellite imageries to know it the band characteristics in terms of the river band length, meander width, the radius of curvatures, and what could be the 10 lambda, the streamline deviations in the river band, the sediment characteristics like ds, the silt number, sediment concentrations, all either you compute direct measured directly in the river, or we can estimate some other data when you have that. So, definitely the river survey plays a major role to find out the river, the variables in terms of flow variables, sediment variables, and the meander variables. That is what we get it data, and if you look at the in terms of degree of freedoms, what are there in the flow, that the discharge, width, flow depth, velocity, perimeters, slope, okay. And also the for the river band you can have a streamlines deviations. For the sediment part, we can have particle size distribution value, silt number, sediment and concentrations, the meander length, width, radius of curvatures. So, we can get a large number of data if I do the river survey using go to the field, collect the data, or we can use a satellite imageries to estimate some of these characteristics from satellite data. Nowadays, you know it is quite easy to get the satellite data as a Google Earth movers are Google Earth is there, and many others satellite data providers are giving a free data set to characterize in the river in terms this. Now, if you look at that, what did they do it? They basically targeting the regionalizations. Can we establish the relationship between independent dependent variables? Okay. Anyway, you can expect it that the independent variable like discharge, the dx and the silt numbers can be the independent. More than that, we do not know it. So, that way if you look it by just looking this data, so discharge which is easy to measure it, and you can have a DS value, you can have a tau star, the sealed numbers, and we can try to look at whether we can establish the relations with other dependent variable like flow width, depth, the velocity, the perimeters, or the sediment concentrations, or we are looking at what could be the meander platform in terms of radius of curvature, in terms of the length, width, whether we can have established the relationship there. And the questions comes that can you obtain a statistically significant relationship among the flow variable, sediment variable, meander dimensions at a regional or the global scales. If I talk about the regional scale, can you develop the relationship for the Ganga, Brahmaputra, Meghna systems? Can you develop the relationship for the peninsular rivers, or can you develop a relationship which can hold good for at the global scales? So, all these bigger questions mark people, lot of research has been going on to find out whether they are regionals. What you generally do it, there are regionalizations. If I summarize that, basically it is a data mining concept. This is data mining concept, people nowadays talk so much. Okay. So, data mining concept, you have a huge data measurement of the flow variable, sediment variable, the measuring characteristics at different part of the rivers at different time intervals, at the equilibrium stage, the stage where the banks are quite stable, okay, or there is not a significant order of change is happening it. If you look at that part, we can establish the relationship using the data mining concept. Okay. Very basic is correlations analysis, visual 3D plots. There are a lot of data mining algorithms nowadays available, and those things we can integrate it and evaluate the relationship. What it happens? What is the known empirical relationship with us? Lexis equations. We will talk about that. Lens equations 1955, 1929, SCOMS 1963, all these relationship I will talk about. Leopold relationship 1964. So, these are the relationships we got it after doing a data mining of a huge data what we collected from the river level, at the reach levels, at the different part of the world, and we try to integrate it either at the regional scale or the global scales, try to look at whether we can establish empirical relationship between dependent variables and the independent variables of a river systems. If you look at that, try to look at that this river behaves differently. There is a concept of equilibrium concept is there, which is a lens concept, the Lexis equations concept will come it. Variational problems also there, they consider is a minimize the energy dissipations concept follows through the variations is the Julian 1985. The large scale ADs concept, nowadays people are talking about all these forces, what it happens it that due to the extreme flood events, it creates a large scale ADs, the turbulent structures what we discussed previous classes, that structure is responsible to have a formations of that. So, that is the reasons there are the large scale AD concept which is Allen and this Discharge. Recently, we also introduced a entropy concept for the river morphology, which you can follow it, and some of the papers also will discuss in the next class that how we have brought it a concept of entropy into the river morphology analysis. That what we will discuss it, but if you look it as a summary, what we are understanding that we need to have a river survey. We should have a quality river survey data, that is what is mattered to us. If data is not having a quality data, we can land up with empirical equations which are not statistically significant. we should identify the variables, flow variables, sediment variables, meandering characteristics and much more. We can look at recently there are a lot of data mining algorithms are there, and the correlations, visual 3-dimensional plots which are there nowadays, any spreadsheets, Microsoft spreadsheet, and you can establish the empirical relationship what we got in almost 70 years back. Those things we can look at, but there are new concepts which are coming it, starting from equilibrium to entropy. That is the basic idea when you do a empirical relationship. So, try to understand it. The empirical relationship of a river system talks about the river behaviors, which we do not understand at the particular time scale or the spatial scale. That the idea is, if it is there is a empirical equations. Let us revisit it, Lexis equations. Again I want to revisit this Lexis equations for you to, because this is the equations we so frequently we have been using it river protections work. So, Lexis equations, if you look at that, it identified the basically the velocities, area, the hydraulic radius and the P, which is the which are dependent variables, is a functions of discharge and silt factors. The silt factor is a functions of particle size, D50 value, functions of particle size distribution. So, this is a silt factors, okay. And these are all conducting a series of experimental data from the canals in Indian subcontinent, undivided Indian subcontinent. Okay. So, if you look at that, if you look at this Lexis formulas which is widely used, it has still has a strength like many equations. It has represent the lumped response of a equilibrium reach of the river or the state reach of the rivers, where the dependent variables like the velocity, hydraulic radius, area, perimeter and the slope is a functional of Q and F1. Q is discharge, F1 is the silt factors. It is just a determining concept. The equation has not come up just like that. They have done thorough analysis of the data using way back in 1929. Okay. We did not have a much computer that times, okay. But this is a data analysis concept. That is the same concept we are using it with supercomputers now, but there is a data analysis concept where it has established the relationship between dependent variables and the independent variables. Independent variables here defined as about the sediment transport, the D50 values and the discharge, the Q representations. And that what you have the velocities, hydraulic radius, area and the parameters. So, just you look at the velocities depends upon for equilibrium channels as a Q as a power relationship with 1/6, okay. And there is a factors F1 factors are there which is 1/3. Same way if you look at that hydraulic radius has this the coefficients. If you look at these, most of the coefficients are simplified in terms of 1/6, 1/3, 5/3 or 1/2. That is basically the perimeters representing Q to the power half. It is too easy to remember it. The P is equal to 2.66 Q to the power half. It is very easy. If you look at these equations, what we rewrite it, the P is equal to the perimeters is equal to weighted perimeters is equal to 2.66 times of discharge square root of discharge. Okay. So, that means it is just depend upon the flow. So, the perimeter of the river, weighted perimeter of a equilibrium channels, it depends upon your only the discharge value, only the discharge value. So, if you look at that, and that what is a power of 1/2.5 square root of this. If this very wide river, okay, the P will be close to the width of the rivers. So, that means for a wide river like a Brahmaputra or Ganges, the width is just a function of the discharge, that is all. It does not depend upon the particle size. So, how can it happen it? But it is the relationship after doing the data mining. We do not know it because these are the data. The canal level data is collected from the field levels, then done the statistical analysis like the Manning's equation, the Lexis equation has a lot of strength. And if you look at that part, the same way for the velocity, the hydraulic radius will be for a wide rivers, it will be close to the flow depth. So, that means the flow depth has a functions of q and f, and this having a functions of q 1 by third and f 1 minus 1 by third. See, if you try to understand it, how these functions has come up, and these are data mining. After doing it, so called today's we talk about data mining concept. Similar way, they collected data, they did the outlier analysis, they did visually all these equations fittings, and then they try to bring it the relationship which might have taken few years to bring these equations. It is not a few days like what we have now computing facilities with Microsoft Excel, spreadsheet or any statistical tools. There was no tools, no computers, but how they derive this concept through the data mining, okay, collecting relevant data, conducting all these things, and this is still holds good still in India, because the regional equations it is quite valid for the Ganges, the Brahmaputra alluvial systems. We use these equations as it being developed for a regional scale. We will discuss much more about this when you go for next levels of regional equations. Now, if you look at the next part, how you define it is the bank full discharge. If you look at that, you can have a rivers like this where you have the floodings, and that bank is not at all having any levee. But there will be the conditions that levee within both the banks, okay, because the water will flow it during the flood, floods both the banks. If it does not flow both the banks, then you will have a outer bank leaves, or if you have a leaves on both the banks, okay. This is a natural levee, okay. Natural levee processes are there, no levee, natural levee process in both the banks and the outer bank leaves. So, if these the conditions, now we have to look at what is the bank full discharge. The natural leaves resultant from deposition of courses of the suspended loads on the flood plain adjacent to the channels. That is what it happens when extreme flood events comes, the flood of 2 years, 5 years return period, the most of the water goes to the flood plain area. As it goes to the flood plain area, thus also it goes with the sediment loads, and that sediment start the depositing, and because of that depositions it creates a natural embankment. That is what is called natural levee. It could be both on the bank or outer bank, or there is no levee formations. Now, if you look at that, we also call about dominant discharge, because the single discharge may not represent it, that it depends upon sufficient magnitudes and frequency to determine the dimension geometry of a alluvial channels. Just time to repeat it. The dominant discharge is that the sufficient magnitudes and frequency, the occurrence, okay, to determine the dimension and geometry of alluvial channels. Okay. In this lecture, so we are not going more detail about dominant discharge, but the hydraulic geometry relationship, the dominant discharge is taken to bank fold discharge, which is having a return periods about 1.5 years. That is what is there. So, that means the bank folds discharge by conducting a thorough analysis is found to be a 1.5 return period flawed discharge. What does it indicate? It indicates is that if it is a bank fold discharge happens in the return period of 1.5 years, that every 2 years we are supposed to be in a natural reverse, we should have a flood in the flood bank plane. Every 2 years intervals you should have, that is the nature of the flow. We should have the floods on the flood plains. So, when you do the embankments, you try to understand what we have been doing it, because we are confining the rivers, and as we confine the rivers, you know that how the sediments happen. But naturally the river creates its flood plains, and flood plain inundations happens at a rate of a 2-year return periods. That means every 2 years, if we are living in the flood plain, if a river as it in natural conditions, we should expect one flood event. So, if you look at that, that is what the natural conditions, but as we modify the conditions, that is what we should try to understand what we are doing it. But naturally what it shows that the bank fold discharge is equal to 1.5 return period flow. That means 2-year return period flow flood in a rivers, it is supposed to inundate the flood plain area, supposed to inundate the flood plain area 3 years, 5 years and 20 years, no doubt it will be inundated more larger area. So, this concept can help us to understand how things are happening at the river scales, and that is what is a regionalization idea, that it has a return period of 1.5 years. But no doubt we should do a regional studies to find out whether it is a 1.5 years or 2 years for Brahmaputra river or Ganges or the peninsular rivers. Those research studies to be done to look at what is happening whether it is 1.5 year return period, that is okay for us. Now, if you look at, if I go for next levels, we try to look at the relationship, the basic relationship. Again, we look at a simple continuity equations and the flow resistance equations. Okay. If you look at these simple continuity equations, which is the discharge is area into the velocity. Here the W is a width, W is width of the river, and A stands is a flow depth, V is the velocity, then you will have the discharge into WHP, so area into velocity. Okay. But if you look at the flow resistance equations, okay, which takes care of all the near boundary, near bed turbulent structures and all, we can establish a relationship with a velocity with H by ds. So, that means ds indicating for us if it is a river bed, these are the river bed, H is the flow depth and ds is the particle size. Okay, if you look at the stones or boulders are there for hilly rivers, you are looking at submerged relative submergence H by dx to the power exponent of m, which also depend upon H by ds. Okay. It depends upon the relationship between this, okay, whether it is a submerged, what is the difference? H is much larger than ds, these values will be the larger value. Is a less, you will have these things. Just you look at the relative submergence is value indicating first. Then if we have the slope, you have a flow depth, then you have the coefficients indicating for us the resistance flow. So, we have the continuity equations, we have the assuming the velocity is going on as a flow resistance equations, you can have this C, and this power exponent m is depends upon relative submergence. Banks are the non-cohesive materials, which is too easy to have a simplifications. No alluvial variables is full of the sands, it is a mixture of silt, clay and compositions of that, but it is okay. If we consider a non-cohesive materials, as we discussed earlier, we can define a sealed numbers which are functions of two components. One is the downstream shear force and weight of the fluid sediment particles. That is what is the sealed numbers or sealed shear stress we talk about. Okay. That is what we discussed earlier. Now, we try to have a relationship, that is what is look at that. You know it, these things, the particles on the weighted parameters of alluvial channels, if you are see that if tau star is less than critical shear stress, if it is more than that, then we will have a motions, okay, it will start entering the motions and the rate of sediment transport increase with the sealed numbers. The sealed number primarily depends upon the flow depth, okay, because ds does not change it, the g does not change it, so specific gravity does not change it, only this h and the s value. So, that is the reasons it is primarily depends upon the flow depth and vertical process of the aggradation degradations in alluvial channels. But if you have flow in a bands, as we discussed earlier, there will be centrifugal forces, there will be streamline deviations, okay, upper streamline deviations will be there, and those things if you relate the relationship, you will get it again h by ds, submerged relative submerged depth, h by w, w is a width, h is the flow depth. So, that ratio and it has a depending upon the BR ratio, which is a constant for us. So, if you look at that, how the flow variables are coming it. So, if you look at all these things, the dependent variables, primary dependent variable is considered is discharge, ds representing of the bed center, and the tau star, the sealed numbers indicating that a ratio between the two forces. One is a shear forces by the weight of the sediment particles. So, these three consider as independent variables, and others we are talking about, and they Julian 1988 establishes that variability of other parameters relatively small. Okay, that is their data analysis and their data mining concept what they got it. These are the three are primary independent variable for them to establish relations with the dependent variables. Now, if you look at the next part, it is quite interesting, which is given by Julian and Wargalen 1995, the relationship between flow depth, width, the velocity and slope is a functions of, now it is a higher versions than the Lexis equations, is a functions of q, ds, tau stars. Q, ds and tau stars, it is a functions, and the power exponent is depends upon m value. Okay. Power exponent is depend upon the m value. So, m is a resistance coefficient which also have a relationship with relative submergence depth. Okay. So, as compared to the Lexis equations, now we are going more details, okay, which is now not only depends upon only the q and ds, it depends upon the sealed numbers, it also depends upon a power exponent, like in earlier case we have a width is equal to 2.66 q into half, okay, q into half. So, width of the river but in this case the width of the rivers has a 2m plus 1, 3m plus 2, plus there is a functions of dx and tau stars. Okay. As we do a data mining, advanced data mining concept, we suppose refine the equations, we get it more independent parameters as compared to the Lexis equations. So, if you look at that, we have this part which is are indicating for us, and S is a friction slope what we have, or the energy gradient, okay, and the flow velocities. Q is a dominant discharge in cubic meters per feet, ds is a d50 in meters, and sealed numbers tau stars and the resistance that. So, what they did it, they established these equations, then they have a relationship between measure and predicted. So, that is the reason when you develop a regional scale things, you need to have a huge data set. Okay. That is what is the statistical analysis. If you look at this is a measured one versus predict for the flow width. So, if it is follow in a 1:1 line, it is a perfect, but it does not happen. For a river database is predictions and the measures should not have a 1:1, because that is the natural variability is there, but their equation is perfect, and that is what is they have the prediction and the width in a meters, width from 1 meter to 1000 meters. Okay. 1 meter to 1000 meters, it is 1 meter river width to go to 1000 meters. Still you can have a relationship of width in terms of discharge, ds and tau stars, and it can follow these functions, and it also showing this statistical significance band. The same way flow depth, which varies from 10 minus 2 to 10 to the power 2 100 meters. Okay. Whenever you see the data in a river case, please try to interpret, then you can have a interesting knowledge about the rivers. River speaks out the truth through this data. So, we should interpret the data more extensively, look at the range. The measured is a 10 minus 2, which is a centimeter levels, goes to the 100 meter, and most of the rivers are in this range. Okay. Most of the rivers are up to 10 meters or the 12 meters, not more than that, and that data set its false is here, and which is a predicted range, and that is the presence. So, with this the Julian-Weisgert's relationship in terms of flow depth, width and velocity and friction slope, we can, the velocity has a much more variabilities, which is a meter per second, it goes up to 10 meter per seconds. Okay. That is what is maximum velocity can happen it. Okay. This is a 1 meter per second, and it can have a 4 meter, 5 meter per second. So, that is what as I said it earlier, the maximum velocity you can design for a river training works. We look interpreting this data, we can consider from this data as it is a measure, you can have a roughly 5 meter per second, because we design for stream, because many of the times in a river systems we do not have the data, and we cannot wait for another 30 years to collect the data, measure the velocity, but we can have interpret the knowledge about the rivers from elsewhere as a regional studies, like as it is indicating here the river velocity which we need it many of the times, it can go as high it's 5 meter per second or 7 meter per second, not more than that. Okay. As the data recording is showing it, because we look for maximum, and similar with the flow depth also in this. Okay. And if you look at that way, the slope also, if you look at the predicted and these things which is more statistically significant band, it's follow it as compared to velocity. So, it all says that how much of uncertainty is there from this scatter plot when you try to establish this relationship, the regional relationship in terms of flow depth, width, velocity, energy slope with respect to Q, ds and tau stars, and these are the data is collected at the river levels, okay, at the field levels, and with the comparisons with a measured and predicts shows us that how good the relationship. If you look at these things, you can say that the velocity can have a lot of uncertainty in measurements, measurement and the predicteds if you look at this equation as well as the measurements, but in terms of depth and width and the slope we can have a not much that significant order of uncertainty is involved. Now, if you look at other very interesting things are there, if you look at this channel width, okay, this is very interesting figures. If I plot it, discharge versus channel width, okay, which varies meter 10 minus 1, it is almost a centimeter levels, the width can go to 10 to the power 5. That means almost a 10 kilometer width, like Brahmaputra rivers, okay, like Brahmaputra rivers, okay, 10 kilometer width, and it can have a 1 kilometers and it can go to the 10 kilometers width, okay. So, if you look at that part, what it is indicating your discharge, if you look at that, just look at the discharge 10 to the power 4, okay. So, that means discharge can go up to 10,000 meter cube for a second. This is a very good relationship and we can interpret a lot of things. These are the data at the river compiled all over the world, plotting between channel width and the discharge. So, if you look at that, if the width of the river is 1 kilometers, it can go as high as 10,000 meter cube per second, which is normal for Brahmaputra rivers, and if a width is increasing it up to 10 kilometers, the discharge can go as a level of 10 times, okay. That means 0.1 millions or 1 lakh meter cube per second. That is the strength of the Brahmaputra rivers, as we can see the width of the rivers, and you just see the width of the rivers and we can know it approximate range of the discharge, because these are the data is plotted for original river. So, if you have a 10 meter width, you can say that you can have a in log scale is a 10 meter cube per second. So, this is a very interesting data which is compiled in 1983 by Kelleran and Charles. For a river specialist, the width of the river we can measure from satellite data and we can know it what could be the average discharge is flowing through that. That is this plot we can use it to know it estimated discharge ranges, okay. That is what is a scale, as I intentionally representing you try to interpret this data, the discharge versus the channel width, okay, as its width varies from centimeters to go to 10 kilometers or 100 kilometers, okay, these are not possible, okay. So, maximum range is 10 kilometers, more than lesser than that, and you have a discharge with a 10 to the power 5 meter cube per second, okay. 1 lakh meter cube per second. So, Brahmaputra discharge is 72,000 meter cube, then maximum highest 100-year return period discharge is much larger than that. So, if you look at that, this data across the global level, it indicates for us to interpret the knowledge, the relationship between channel width and the discharge. That is what, if you look at that, the average flow depth is h in meters, surface width w, and if you have average velocity v, equilibrium slope if you establish is a function of q ds tau stars, and if you use the m equal to 1 by 6 using this Manning's equations, these equations again you can modify it, you will get a relationship, approximate relationship between flow depth, width, velocity and the energy slopes and the energy solve, which is a function of that. But just trying to have a representing you that if you look at that, the Lexis equations talk about the width is a functions of a constant and functions of 1 by 2, that is okay, is power function of 0.5. The same thing here is a 0.53. No doubt we improve the equations, but more or less the power exponent of this relationship, it remains more or less the same. That is the things you can try to understand it with the different things. So, in time we are evolving regional river relationship, but more or less the power exponents are within the ranges. Okay. That is what is Lexis equations is 0.5, and whereas the Julian equations is 0.53. So, it is not significant difference, not significant difference, but there is a tau star and ds is there, which may have a slight bit difference is there. Now, if you look at the next level to interpret it, or many of the times if you know the discharge and D50 value and we know the Silt numbers at the beginning of the motions, can we compute the downstream hydraulic geometry? That means, we need to compute depth, width, the perimeters and the velocity and the slope. Discharge known, D50 is known to us. The problem is here, m is a function of dx, okay, and the h. M is a function of relative submergence depth, which is a function of h by dx. So, that is the reasons we will assume a flow depth, compute the m value, then again you recheck it, whatever the h values are coming are the same. In this case, we first resume the h equal to 1 meters, compute the m values, then you put the regional equations of that m value, compute the h. So, we found it, the assumed values is 1 meter, which is assume it, but estimated this, that means there is a lot of difference. So, we again hit and trial methods, we change the h value, compute m value, again you compute the h from the regional equations, whether that two differences are there or not there. If not there, then you can assume that h value. That is the we do it. So, if you do it this repeatedly calculations of this till it converts the h equal to 1.49, m equal to 0.17 and which gives h equal to 1.51, the difference is not much difference. If that is the conditions, we can fix up that and then you can compute m equal to 0.172, flow depth, width, velocity and the slope, what we get it using this empirical equations. So, this is what we can use it from D50 values and all to compute is the flow width, the velocity and the energy slope gradients. That is for this downstream hydraulic geometry. Now, if you look at very interesting part graphs, which is we many of the times we just you to show it the Brahmaputra rivers, one of the river where everything changes very fast, river planform, river geometry, sediment transports is are too dynamic. You can see this combined type of braided channels. Okay, nowadays it is not a difficult. Any satellite imageries, Google Earth imageries, you can see it how dynamic this from the rivers in terms of series of channels. Okay, in terms of series of channels, what we have, it makes us is a very interesting part. The how the channels are changing it. Okay, still you have a challenging task to understand these rivers. Okay, in a sand bed, braided river systems in the world over the world, this is a typical rivers. And if you look at it, how this progressive development of channels, okay, if you look at that part, really it is indicating for us, just try to interpret these figures. Okay, you just check it, this is the channels, there is a channels and there is a island formations. Next part you look at the channel is here, there are a lot of sand depositions, the islands are not there. Then further you come it, these two channels are activated, there are island again formating in between that. and you go further, again this is again channel formations, all these things are happening, again island formations are happening. If you look at these time history lines of timelines of a river Brahmaputra planforms, which is too dynamic, and that is what is makes us to understand these braided rivers, whether does it follow any science or does it follow any energy dissipations concept. All these are big questions. Okay. So, the basic idea is like if you look at that, how the river has a dynamicness and how this cut off the island, consequent the bank erosions process which is happens it so dynamically in Brahmaputra rivers, you can look it. These are quite interesting and quite challenging for us. Now, if you look at how does formations happens as a bars in alluvial rivers. If you look at that, the bars generally a large bed for configurations in a alluvial bed deposits. So, if you look at that, if you have these channels, okay, if you look at these figures, the channels will not have a straight, okay, there will be a meanders. Okay. Because of these meanders, you will have a bar formations. Okay. These are called point bars, alternative point bars, and this is the thallic line, the defaced channels. This is the thallic line, and you can have a alternate bar formations will be there, and these bar formations can have a wavelength, which is a 2 pi times of channel width, okay, closely 7 times, okay, or 3.6 times of width. Okay. You just try to understand it. Okay. The formations of alternative bars with a 2 times of phi of W, or we can say it as close to the 6 times of W. Okay. Do not go to too precise. Okay. So, 6 times, okay, 6 times of width of channels. You can see this, the length from this to these points. If you look at that length formations of these wavelength formations of alternating bar, which is a as close to the 6 times of width of the. So, that is what is accelerating part. So, if you look at that, there will be high flow conditions, there will be transport, the stabilize with the vegetation grow from the islands, as I showed the photograph of Brahmaputra rivers. It is a proud numbers which is high in these channels, okay, and the silt parameter is a close to incipient motions. The height of the bar can reach to the flow depth. So, height of bar can actually exposed into the higher levels, that is the conditions can happen it. Now, if you look at next one, very interesting, if you look at this point bar formations, again I want to tell you to just sketch the figures to understand the river mechanics. Is that if I have a river, you will have a point wire formations, okay, point wire formations will be there. There will be a pool, there will be the point wire formations, river crossings point will be there, and if you take a cross section at A dash, which is just a crossovers, you can have a as close to the parabolic shape, but when you have a near the thallic line, near this point bar, you can see the depositions, you can have a secondary current and you can have a defaced channels. Okay. So, as we discussed earlier, so you can see that lot of sedimentary depositions happens it. The formation induced by the secondary current, that is what we try to show in many times, how the secondary current formations will play the major roles. Inner bank will have this point bars is found in the inner banks, okay, associated with the erosions of outer bank and lateral migrations of the rivers. So, river also have a lateral migrations, and if you look at this part, it also go for a cutoff. Okay. It will have the cutoff. So, then this island becomes mid by island, mid channel point bars, and then you can have the cutoffs. Okay. The cutoff shoot off will crowd it, and truncated the point bar also referred as a middle bar. Okay. So, you can have these conditions, and just sketch the figures of the rivers plan forms and try to understand it, how the secondary currents are happening, how the plan forms are happening, how the thallic line shiftings are happening, and the cross section. That is we should understand it looking the river platform. Now, if you look it, many of the times we have the river and the tributaries are joining it. So, you can have the depositions which is called the tributary bar formations. Like for example, if you look at these cases, okay, two rivers are joining it, and if you draw the streamlines and all, the flow will come like this, okay, flow will come like this. So, there will be a erosions, the depositions also deter. So, because of this joining the two alluvial rivers, both are feeding the sediments to this reach, and there are the thallic line, the shifting of the channels, and because of that there will be a erosions and the depositions, and there will be a tributary mouth, depositions will happen it, also the tributary ones will be there, and because of so much erosions, depositions happens it will also create a mid channel bar. It will create the mid channel bar. If I take a cross sections, if I just take a cross sections, if you look at that A dash, B dash and C dash, the three cross sections. If I look at that, the shape of the A is coming like this. Okay. So, there is a thallic line, B dash, there is a depositions, tributary bar formations, then this at the C dash, you can see that mid channel depositions are happening it. So, two channel formations are there. So, the tributaries we can have a sometime middle channel bar formations. So, the tributary junctions can have these conditions. So, we should try to understand how the flow sediments, the erosions or depositions are happening it at the two confluencings with the river and the tributary in alluvial zone. Not only that, if you look at that, this is a confluencing or streamlining of confluences of both the streams, and if you look at the like a Brahmaputra rivers, also in the top you see it is not a one channels, it has a lot of sub meandering is there. Within the meanders there is a meanders. Okay. So, you can see the river in the top, but at the bottom levels there are the sub meanders are happening it, which if you do not have a cross section data analysis properly, we cannot find it. There are very smaller meanders are happening it. So, it is quite interesting and quite to look at research study that how does it happen it, the meanders and the sub meanders, and those sub meanders how the morphologically they are active, whether these sub meanders also accelerates the bank erosion process. Does it the sub meanders play a role for morphology? All the big questions still we do not have an answer for that, because there is not much study has been done it for, and these sub meanders are visible in Brahmaputra river in many part of the rivers stretches. That is the reason it is still it is a complex rivers morphologically to try to understand it, how the compositions of meanders, sub meanders, the braidings are happening in this complex river. Before leaving this lectures today, let me talk about the case study 1, which impact of the river interventions of alluvial channel morphology. So, we conducted a study and we published in ISS Journal of Hydraulic Engineering in the last years. We try to look at what is the impact of Rangali dam, the dam structures on the Brahmani river morphology. We try to look at first order analysis to do between upstream and downstream gauging stations, second order analysis which look at these seasonal stream powers evaluations with the temporal variations of Bryce index and the cutoff length of a critical river reach. What we found is that if I do these flow durations and sediment durations curve analysis, the lean season discharge has increased 300 times. Okay. Because of this Rangali dam, okay, the lean flow discharge has increasing trend. Okay, that is almost 300 times. Okay. The peak suspended load sediment concentration has decreased at the downstream reach, which expected because it is a reservoirs are there. So, because of the reservoir, the peak sediment concentration has decreased the downstream reach. Okay. The sediment decreases, the seasonal flow is increasing trend. the flow is increasing trend, where is, so you can have these things. And what is it with that? The seasonal stream power analysis, increasing trend of free monsoon stream to 56 or 300 watt per meters to 800 watt per meters. So, energy dissipations has increased, okay, pre monsoon stream powers. The plant forms alteration study shows that there is a breeding initiations, which is earlier is breeding index is 0.14 in 1975, it has gone to 2.33 in 2016. So, well, almost 40 years. After the 40 years, the breeding index, which is indicating the Bryce index, which are indicating for us how much a river is breeding it, that is what it happens. Earlier it is not a breeded rivers, and it is going towards a breeding after the 40 years implementing these dam products, and there is a cutoff mid channel bar predominantly post dam periods. These are, we are summarizing these things. If you are interested, you can refer to this paper. Next part, how this is the upstreams, the sediment discharge and all not change much, but there is a downstreams. If you look at the discharge and the flow distributions curve has changed it. Not only that, it has significantly increased the Bryce index is 0.14 to 2.3, and you can visually look at how braided channel formations happen it. And if you look at the cutoff length, which is increasing still like this. So, that is the curve. So, river meanders to, it is going to the braided forms. So, we should try to understand it faster or second order analysis because of the dam structures what we are creating it. We have done some interventions, and that interventions how the river is responding. That is the questions we always should ask it, and we should monitor the river at the different levels. Just let me conclude this lectures talking about that the watching the Brahmaputra river braiding is a truly a piece of art, which we partly understood, partly not understood it. Thank you very much for this.